Have you ever looked at a complex circuit, seen its behavior described by intricate differential equations, and wished there was a simpler way to understand what is happening inside? Electrical engineers often face the challenge of analyzing circuits where components like inductors and capacitors introduce dynamic behavior. The key to unlocking this understanding, particularly how a circuit responds over time, lies in bridging to critical domains of analysis. To convert a circuit's description from the frequency domain back to the time domain, you primarily use the mathematical technique known as the inverse Laplace transform. This powerful tool allows us to translate algebraic expressions representing circuit behavior in the complex frequency plane back into real-world time-dependent functions. The reason we employ the Laplace transform in the first place is that it converts challenging integral differential equations, which describe circuit behavior over time, into much simpler algebraic equations in the frequency domain. Solving these algebraic equations for currents and voltages is significantly easier. However, the final result is in the frequency domain, often denoted by a variable like S, and does not directly tell us how the circuit performs instant by instant. The inverse Laplace transform acts as the crucial bridge, taking these frequency domain solutions and transforming them back into time-dependent functions, making them meaningful for practical circuit analysis and design. This transformation relies on properties like linearity and uniqueness, ensuring a direct and predictable path back to the time domain. The process typically involves a few systematic steps. First, ensure your circuit's voltage or current is expressed as a proper rational function in the S variable within the frequency domain. Second, if the expression is complex, especially with higher-order polynomials, you will often need to apply partial fraction expansion. This technique breaks down the complex rational function into a sum of simpler terms, each of which has a known or easily derivable inverse Laplace transform. Third, once you have these simpler terms, you refer to a table of common Laplace transform pairs. These tables list various frequency domain functions and their corresponding time domain equivalents, such as exponential decays, sine waves, cosine waves, and step functions. Fourth, you then combine these individual time domain functions to obtain the complete time-dependent response of your circuit. Many software tools can also perform these transformations numerically or symbolically. Understanding this conversion is not just an academic exercise. It is fundamental to predicting a circuit's transient response, which describes its behavior immediately after a change, and its steady-state response, which is its long-term behavior. It allows engineers to analyze stability, determine critical damping, and even identify issues like oscillations or ringing. Furthermore, the concept of poles and zeros in the frequency domain directly informs the nature of these time domain responses, indicating the stability and general behavior of the circuit. For example, poles in the left half of the S-plane correspond to stable, decaying time domain responses. Mastering the inverse Laplace transform provides you with a profound understanding of how theoretical circuit models translate into observable physical phenomena. This ability to move fluidly between the frequency and time domains empowers you to not only analyze existing circuits, but also to design new ones with precise control over their dynamic performance, ensuring that your mathematical models accurately predict real-world behavior.